We're going to go over the review for nuclear and balancing test. So first off, for an alpha particle, that's basically a helium nucleus. Okay, it does not have the 2 electrons. It just has what's in the nucleus of the helium atom. For a beta particle, that's basically an electron. And for the gamma, that is a high energy photon. Particle of light, basically, that has no mass, no charge, but lots and lots of energy. Okay, symbols. Okay, alpha can be the Greek letter alpha with a 4-2, or it's a 4-2 He. The top number 4 being the mass number, the bottom number 2 being the atomic number. For a beta particle, we have the B for beta, and it's a 0, -1. Or you will see it as an E, lowercase e by the way, and then a 0, -1. And then the gamma symbol kind of looks like the fish symbol, but it's on its head, and it's 0, 0, has no mass, has no charge. For the beta, no mass, relatively speaking, -1 for its charge. So those are the symbols that you may see on the test for the different particles. Okay, 3, what is the change in atomic mass number? Now please note, you have to pay attention. Atomic mass number, okay? The mass number is not the atomic number, it's the one, so this is the one on top, okay? And so for the one on top, the alpha particle will decrease by 4. Okay, that same 4 that you saw up above, the mass is going down by 4. The beta particle, there is no change in the mass number. Now, if the question is atomic number, not atomic mass, but atomic number, then the alpha particle actually decreases by 2. The beta goes up by 1. So you have to make sure and catch whether they're talking about the mass number, which is the top one, or the atomic number, which is the bottom one. Okay, penetrating power, which also goes with which is the most dangerous. The more it penetrates, the more dangerous it is. Basically from greatest, this would be gamma, and then beta, and then alpha is the least penetrative. Okay, what is the charge? Alpha particle. Again, it's a helium nucleus, so no electrons, +2 charge. Beta particle, -1. Gamma, 0. 6. What material is necessary to stop the different particles? Well, for alpha, skin, sheet of paper is good enough. For beta particles, wood, aluminum foil is good enough. But for gamma ray, you need inches of lead or feet of concrete. So you need a lot of protection for the gamma. What particle decomposes to produce the electron of beta radiation? A neutron. Basically, the neutron produces a proton and an electron. The proton stays in the nucleus, the electron gets emitted out of the nucleus. All right, some balancing of nuclear reactions. Remember that the top numbers on either side of the arrow have to match up, and the bottom numbers have to match up. Top number, here I have 10 and 1, so that's 11. So on the other side, I need to get to 11, 2. So that means that's a 7. Bottom number, I have 5 and 0, so that's 5, 2, and 3. Gives me 5. Number 3, that's atomic number 3, means that this is a lithium isotope. Because number 3 is lithium. In number 9, I have 202 here. So on the other side on top, I have to have 202, which means 198 plus the 4 will give me 202. I have to have 81 on the bottom. I already have 2, so this has to be 79. 79 and 2 would be 81. And this will be gold. Number 79 is gold. Number 10, 209 to 209. Top has to be 0. 82 went to 83, but the total between these two has to still be 82. So this has to be a -1. So this number 10 is a beta particle. So, any questions on nuclear balancing? And of course, the test is all multiple choice. You just make sure both top and bottom match, and you'll be fine. Okay, 11. What do the letters C and D represent? C is the mass number. D is the atomic number or charge. And the reason I say or charge is, for instance, for a beta particle, that's not its atomic number, but it is its charge. Okay, couple of half-life problems. If the half-life of a radioactive material is 12 days, how many days will it take for 3/4 of the original amount to be decayed? Well, let's imagine for a moment, we're going to make it easy. Let's just say that we started with 20. Okay, so after one half-life, it'll be down to 10, which means half is gone. Okay, after the next half-life, we're down to 5. How much is gone though? 3/4 is gone. Okay, because we lost a half in the first one, and then we lost half of a half in the second one. And so half plus 1/4, that's our 3/4. Now that was 2 half-lives. So 2 times my 12, 24 days to have 3/4 of it gone. Okay, again, we lost half after 12 days. We lost half of what was left after another 12 days. Okay, half of a half is 1/4. Half plus 1/4 is 3/4. So it took 2 half-lives, or 24 days in this case. Okay, 13. We started with 20. We got to 5. And that was in 32 days. It wants to know what is the half-life. All right, well, first off, we went 20 to 10 to 5, kind of like what I did in the previous problem. That's 2 half-lives. So 32 divided by 2, 16 days is how long the half-life was. In other words, after 16, we were at 10. After another 16, we were at 5. So 32 days total. Okay, 14 is sort of a trick question. It's like, can you read? The half-life is 120 seconds. So how much is left after 120 seconds? Half. That's why it's called half-life. So if I had 100, half of it's left after 1 half-life. That's it. It's just, do you understand the definition of half-life? After that much time, only half is left. Okay, what is the notation of copper with an atomic number of 29 and a mass number of 65? It's kind of like what you have up above, where we were back up here doing these problems. The top number is the mass number. The bottom number is the atomic number. And then you have your symbol. So that's how you would do the notation of copper with a mass number of 65 and an atomic number of 29. Okay, 16. What does the nucleus of an atom of Fe55 contain? Well, first off, Fe has atomic number 26. So that means 26 protons. However, 55 subtract the 26 gives us 29 neutrons. So what's in the nucleus? 26 protons and 29 neutrons. Again, for nuclear, we're just worried about what's in the nucleus. Okay, 17 is similar to 15. What's the notation? Well, for carbon 12, it's that. For carbon 14, it's that. They're both number 6. The atomic number is not changeable for each element. So if it's carbon, it's got to be number 6. The top number can change because different isotopes have different number of neutrons. But the bottom number is fixed for each element. All right, so 18. What's the same and what is the difference in subatomic particles between the N15 and the O15? Well, their mass number is the same. Their atomic numbers are different. So what does that mean for the particles? Well, for nitrogen, because of the 15, it's got 8 neutrons and 7 protons. It's number 7, so it has 7 protons, and 15 minus 7 gives it 8 neutrons. For oxygen, 15 minus 8 would be 7 neutrons, and since it's number 8, it's 8 protons. So in terms of their subatomic particles, and that always means protons, neutrons, and electrons, their subatomic particles, they have a different number of neutrons and they have a different number of protons in this case. The nuclear force is what keeps the nucleus together. Small change in mass is multiplied times c squared as part of E equals mc squared. That c squared is 10 to the 17th. So a tiny bit of mass change in combining 4 hydrogens to make 1 helium, for example, is then multiplied times 10 to the 17th power, and that's why it's so much energy. And it's using Einstein's famous equation E equals mc squared. Now, without doing too much in terms of your drawings, basically fission is a big thing breaking apart into little things, and fusion is little things coming together to make a bigger thing. So here's fission breaking apart, and here's fusion. Okay, balancing of equations. Always start with things that are different. For example, here I look at the oxygens. There's 2 on this side. There's 3 on that side of the arrow. So if I start off by switching the numbers, 3 and 2, now I have 6 on both sides. 3 times 2 oxygens, that's 6 over here. Because remember that basically when I put that 3 there, it's like having 3 O2 molecules, but it's 6 oxygen atoms altogether. And then over here, by putting that 2 in front of the Al2O3, that's basically saying I have Al2O3 and then another Al2O3. But again, that's still 6 oxygens. And then once I do that, I have to have a 4 there to balance out the aluminums. Now you're going to basically have answers which say things like 4, 3, and 2, or maybe they go 2, 3, and 2, or 1, 3, and 2. And so you got to pick the right ones. Remember, every single element has to match. So 6 oxygens, 6 oxygens, 4 aluminums, 2 times 2, 4 aluminums. Okay, next, have 2 hydrogens, 2 iodine atoms. Over here, HI. So 2, 1, 1. Next one, I can look at the chlorines, which are different. So 2 there, 3 there. Now there are 6 chlorines on both sides. 2 times 3 is 6, 3 times 2 is 6. But now that I have a 3 in front of the Ca, has to be a 3 in front of that Ca. 2 in front of the Al means a 2 in front of that Al. Next one, 2 PO4s, 1 PO4. Likewise here I have 2 ALs, 1 AL. So put a 2, 1, 1. Takes care of the PO4s and the ALs. But putting a 1 there means I have only 1 calcium. So I have 1 calcium. Please note, I did not do the sulfur by itself. Okay, I did not do the phosphorus by itself. I just treat the entire PO4 as one thing, the entire SO4 as one thing. And then the last one. Check my hydrogens first. Cut the number in half and see if it's odd or even. 18.5 is odd. If that's true, I put a 2 there. If it's not true, I put a 1. So if it's even, when I cut that number in half, this is where I start. If I cut that number in half and it's even, I put a 1. If it's odd, I put a 2. Now, do the carbons. 2 times 9 is 18. So there is 18. Now do the hydrogens. 2 and 18. 18 and 2. And no, this is just coincidental that these two happen to be the same. That's not necessarily true all the time. Now I check for my oxygens. Here, there are 36 oxygens. 18 times 2 plus another 18 oxygens. Those together give me 54. So I need a 27 there to make it balance. Okay, types. First one, 2 things go to 1 thing. Synthesis or direct combination. The second one, 1 thing gets split apart. So that's analysis or decomposition. Next one, notice single elements in both sides. This side and this side. Single replacement. Next one, 2 compounds to 2 compounds. Everybody's a compound, all 4 of them. Double replacement. And the last one, CO2, H2O, O2, those 3 things, combustion. Now, last thing I want to mention. Okay, when it comes to the names for the different compounds, okay, if it's ionic, like this one, okay, it's the name off of the positive ion, calcium, and the name off of the negative ion, chloride, calcium chloride. If, however, it's a molecular covalent chemical, that's where you're going to have to worry about the dis and tris and tetras for their names.